All right, so for today's notes, we're not actually taking notes on page 108, I should point out. This is just where we're starting. Because on page 108, we talked about the combined gas law, which we use when something is changing. When pressure, volume, or temperature changes, what is the new pressure, volume, or temperature? To do that, the equation is this. The first pressure times the first volume divided by the first temperature equals some weird magic number. And because that weird magic number never changes, it also equals the new pressure times the new volume divided by the new temperature. But I told you, don't worry about what goes in the middle there. Don't worry about that magic constant. Today we're going to. So when I did Lab 17, this is the data that I got for pressure versus volume. And we can see that it is an inversely proportional relationship. So it's basically useless to us because I can't get a slope because I don't have a straight line. At least not yet. In calculus, you can do all sorts of crazy things. But for us right now, not helpful. So instead, I graph it pressure versus 1 over volume on the bottom. Fancy. And now I have a line. And my slope in this case was 0.0201, which is roughly what your slope would have been if you had also been doing pressure in atmospheres. It would have been somewhere around that. Okay, so wait, so if I was doing pressure and volume, that means that temperature was being held constant. The other thing that was being held constant was the amount of gas. And by amount of gas, we mean the number of particles, the number of moles. The mass was also being held constant. But we don't care about mass in chemistry. We care about number of moles. It's been a long time since we've talked about moles. So you might want to look through your notes again. But the super brief thing is this. 1 dozen eggs is a shortcut of saying 12 eggs. 1 mole of particles is a shorthand way of saying 6.022 times 10 to the 23rd particles. So that means 6022 and then 20 more zeros. It's easier to just say a mole. So that means that since the temperature and the number of moles was constant, that means that my slope, which is rise over run, is 0.0201 atmosphere times liters. Okay, well that's a little weird, but that's what I got. If you were also looking at your pressure and 1 over volume graph, the slope has units of atmospheres times liters, or kilopascals times liters, if that's what you measured your pressure in. Now, that magic constant, that 0.0201, has temperature wrapped up in there somewhere. So we're going to divide the temperature out. That's room temperature. I know that my room temperature at this case was 294 Kelvin for my lab when I did it, which gives me a number of 0.0000684 atmosphere liters per Kelvin. Okay, well, I'm not even going to think about what that number means. I'm just going to keep going. Because that number also has the number of moles. So when I divide out the number of moles that were involved, okay, well, wait, so if it's 22.4 moles per liters per 1 mole, and I add 0.02 liters, that means I have 0.000831 moles. If I divide that number out, I get 0.0822 atmosphere liters per mole Kelvin. All right, cool, that's nice, Mr. Styles. So why do I care? Why do I care? All right, well, here's why I care. Here's my other graph, pressure versus temperature. Volume is being held constant and number of moles. If what I said before is correct, that I should be able to do the exact same thing with this graph and get the exact same number. So let's see if it's true. The slope is rise over run, so 0.00367 atmospheres per Kelvin. I'm going to multiply by the volume because it's P times V, and that gives me that ugly number. I'm now going to divide out my number of moles, and I get the exact same number. It turns out, and this is called the ideal gas law, you are now writing stuff down. This is where the writing stuff down starts. Turns out the ideal gas law is that pressure, volume, temperature, and the number of moles are all related together by the same constant. And it doesn't matter what the pressure, what the volume, what the temperature, what the type of gas is, or how much of it there is. The number is always the same. All right, now if we put that into an equation, we get this. PV equals nRT, where P is the pressure measured in atmospheres, or kilopascals, or millimeters of mercury. V is our volume measured in liters. N is our number of moles, measured in moles. T is our temperature, measured in Kelvin. And R is called our ideal gas constant. This gives us an equation that we only use when there is no change. So if I give you a problem where I say, hey, so the pressure, volume, temperature was this, and then I doubled the temperature, there's a change. Do not use this equation. You use this equation, that direction, that equation, only when nothing changes. What is R? Move my face around a little bit. You have to use a different R depending on which pressure measurement you're using. So for atmospheres, you need to use the 0.0821. For kilopascals, you need to use 8.314. And for millimeters mercury, you need to use 62.4. There we go. That's it for lecture, as it were. Now I have 4 example problems for you. What I'm going to do is I'm going to show you the problem. I want you to hit pause. Try to solve the problem. Hit play again. See how I do it. Come on over, Miriam. Come on. Come say hi to my students. Yeah, look at the camera right there.
Hi.
I want you to wave. Say hi, students.
Hi, students.
Say do good at chemistry.
Good to chemistry.
Close enough. Okay, now shoot. So here's your first problem. We'll have a seat. If you're going to hang out, just have a seat. All right.
I want to hang out with you.
Okay, you hang out with me while I'm teaching.
When I'm in school, I want to hang out.
Okay, here. If you're going to be here, let's move this over so we can see you too. Okay.
When? Hello, everybody.
Okay, all right. Shh, you're doing chemistry. What is the volume of a balloon that has 0.45 moles of gas held under 215 kilopascals at a temperature of 300 Kelvin? All right, pause. If you're still watching this, you must have finished the problem. Here's what you do. Hey, shh. First, you got your equation. PV equals nRT. You plug in your knowns. You know the pressure. You know the number of moles. Goodbye. You know the temperature. Oh, you want to say hi to my students too, Derek? Yeah, come here. No? Okay, fine. Wait, hi, Derek. Oh, you don't want to. Okay. Oh, I'm almost done. All right, so there's that. There's that. And there's your answer. Next one. Bam. Next one. Bam. And last one. Shabam. Do chemistry.
Yeah.
Say bye, Miriam.
Bye, Miriam.